Hello, this is Mrs. Hedden. This is Chapter 15, Notes 3. This is notes on the first law of thermodynamics as it relates to PV diagrams. Okay, first a few terminology things. When we talk about the state of something, we're not talking about Alabama, great as it is. We're talking about what state the material is in. And the state the material is in depends not only on its whether it's a solid, liquid, or gas, but also on its internal energy and a bunch of other things. But we can determine this state by looking at certain key properties, what they call state functions, which is not a great dinner to go to, but rather, for an ideal gas, the state functions involve entropy, pressure, temperature, and volume. If we know at least two of those state functions, we can determine exactly what the state of the gas is. The difference between the amount of internal energy between two states is a constant. In other words, it doesn't matter how you get there. So if you have a gas that is in a very excited state and a gas that's in a okay quasi state, the difference between their internal energy is the same no matter how you got that guy excited or how you calmed it down. Okay? So it's independent of the path. The delta U, the difference in the internal energy, is simply equal to the internal energy at one point minus the internal energy at the other point. And that's important because work is not independent of the path. Let's go on. The work done by the system is always considered to be positive. Okay, so we've got that equation down there of delta U equals Q minus W. That's that second equation right here. And if the system does work, that work is positive, and we're taking that energy required to do the work away from the system. So a system will lose energy by doing work, and that's a result of this and that convention. Work done on the system is negative, and a system will gain energy by doing work. So in other words, if you have Q minus a negative work, you're gaining energy. This convention is hard to remember but important, and there are textbooks that will use a different convention, but this is the one that's generally accepted at this level of physics. And by the College Board. So and it's easy to remember that if you're doing work, you're going to lose energy. Therefore, this work has to be positive, so you've lost energy per this equation. If work is being done on you, you're gaining energy, and so this work has to be negative so you can gain energy. That's one important thing. The next important thing is that the work done is simply the area under a PV graph. It's really that easy. Do not confuse it. Work done is simply the area under the PV graph. Remember that, and life will be wonderful. It doesn't matter how you draw your PV graphs, whether it's a nice, simple, straight line like this, and the work would be really easy to figure out, or whether it's a curved line like this, and you're going to have to use calculus to figure it out. One way or the other, the work is still just simply the area under the graph. And then the next step is many processes are cyclic. That means they start and they do something, and then they regroup to do it again. The piston of a gas engine gets gasoline in it, it fires it off, the piston does work on the engine, and then the piston comes back down, and you put more gas in, and you fire it off, and it does work, and then it cools down. So it's a cyclic process. It goes over and over again. And when you have a cyclic process, the total work done in this process equals the area inside the closed loop. This should be cyclic, not cylindrical. Sorry, cyclic. The total work done is the area inside the closed loop. And again, it doesn't matter what that closed loop looks like. It can be real simple, like a square, and that area can be really, really easy to figure out. It can be a lot more complex, and they'll talk about isobaric and adiabatic and all other kinds of terms to describe these different phases. Oh, here we go. Adiabatic expansion, isothermal expansion, isothermal compression, adiabatic compression. Doesn't matter what names they give those lines, it's still the total work done is that area inside that thing. Again, the Stirling cycle, which is a really cool, awesome cycle, doesn't matter what names they give it, the work done by that Stirling cycle is simply the area inside the curve. Using that information, you're going to go ahead and do the ranking sheet 109. So, the most wonderful sub is going to stop the video, hand out the worksheet, and the most wonderful students are going to go ahead and do the worksheet. So we'll pause the video now for a while. So now that you have individually done that worksheet, I want you to get together with a partner, compare the answers, and more critically, why you chose those answers. So get together. We're going to pause the video again while you get together with a partner and talk about what you've done. So go ahead and talk it over. Are you guys really done talking it over? Did you really do the worksheet individually? Did you really discuss it with a partner? Okay, so now I'll tell you what the answers are. We've got what I first did when I looked at well, these are the answers. D, F, C, E, A, B. Okay, that's the ranking. First thing I did is I looked at B. B goes straight down. Is there any area under that line? No way. Therefore, the work done for B is equal to 0. So that makes B easy. The next thing I did is I looked at this guy, D. D was a straight line right here. It starts at P and it goes from 2V to from V naught to 2V naught. Now it's a straight line. The area under that curve, that's obviously got to be the biggest because it's just a nice straight rectangle. The others all kind of cut the rectangle off. So D was the max. So I had D at the top and I had B at the bottom. So then I just had to get the other guys in between. Well, this is a straight line. It makes this kind of triangle. These guys are curved. So I could say, well, let's just compare C and F. And C goes from P naught to P naught over 2. F goes from P naught to something above P naught over 2. So this rectangle is bigger than this rectangle. Okay, so F is greater than C. And then I looked at A and E and said, well, these guys are curved. Okay, but I can still kind of like cut off where the curves are at. And, A is curved to below P naught over 2. So this rectangle is smaller than this rectangle. So I could say, well, E is larger than A. And then it's just a matter of where does E fit in terms of F and C. And you can see C has this, triangle here that's very clear from P naught to P naught over 2. Whereas from P naught to P naught over 2, E is not a straight triangle. E bends in. So this triangle, well, the rectangles here for E and C are the same area. The triangle for E is smaller than the triangle for C. So therefore, C is greater than E, and that gives me my ranking. Woo. Now we're going to have to go back again to chapter 13, which is one of the reasons why I did that, weird, crazy problem where you had to go back to chapter 13 that I did in the last video. Realizing that we're working with ideal gases, we can combine the idea of work and heat loss, gain, and energy loss or gain with the ideal gas law. So if we do work by the system, remember we have lost heat. If work is done on the system, we have gained heat. Well, heat loss is the same as energy loss. Heat gain is the same as energy gain. Okay? And we have these PV diagrams, which we just looked at one, but PV in ideal gases is equal to nRT. Now, in our physics book, because physics likes to distinguish itself from chemistry, we also had PV equals capital N KT. Capital N is referring to molecules or particles. It's a more general summary of the ideal gas law because it's no longer talking about ideal gases. And we could go on and talk about many more things. We don't really usually do that at this level of physics. K is just a different constant than R. Otherwise, they're saying the same things. Pressure times volume is basically, in this case, proportional to the number of things you have times some constant, which is what makes it proportional, times the temperature. Okay? So you're going to combine these guys together to do some more ranking. And with that, you're going to go ahead and try and do ranking sheet 112. So we'll hand it out, the wonderful sub will, and my wonderful students, you guys, will go ahead and rank 112. Stop the video. Hand out the worksheet. Do it. We'll go over it tomorrow. Thank you very much for your time.